first thing we have to do is learn how to do linearization. Okay? It says use the equation of the tangent of that thingy to estimate square root 2. What does that mean? Do you see that square root 2 happens to be, well, this happens to be f of 1, isn't it? If I plug in 1 here, do you see this function gives you square root 2? And do you happen to know the value of square root 2? Thanks to my middle school teacher, he made me memorize square root 2 and square root 3. He had a lot of foresight in middle school. Okay. But then in the olden days when Newton was around, there were no calculators. So they had to develop a way to estimate these things. Okay. So we have a graph of square root function here, 1 plus square root, translate to the left by 1 unit. And if we draw the tangent line right there at 0, 1, it looks like this, right? And 2, well, 1 is right here. This is the value we are trying to estimate. So good. So this is our f of x. And the line, in order to distinguish from f, we'll call it L of x for linear. You know what I'm saying? And then the value right there, you see how close that is to real f of 1? L of 1 and f of 1 are really, really close, right? But linear thing about linear function is we know how to evaluate it. It's linear. It's nice. So let's just find the equation for L of x, shall we? Okay, so point slope form, and we have a point right here, so we just need a slope. And for that, we'll f prime of x, which is 1/2, and then 1 plus x to the negative 1/2 power. Y'all good? Okay, then we evaluate this at 0, which will give us 1/2, right? Too much algebra? Okay, point slope form. So we have y minus 1 is equal to your slope, and then x minus 0, eh? Okay, so our y, which I'm gonna, L of x, which is our y at the moment, is equal to, I'm gonna write it a little bit weird. How about that? Okay, so far so good. Now, so our square root 2, which is what our f of x is. Now, since we don't know how to do it, but it's approximately same as L of x there, square root 1, f of 1 is square root 2, which is approximately same as L of 1. Do you see that? This gap between the two functions is pretty small. So we plug in 1 to here, then we get 1.5. And compare this to this thingy, and see that error is not that big. You know what I'm saying? Okay, this technique is known as linearization. In the book, there's a linearization formula, and you know how I feel about the formula, right? But I will derive the formula nevertheless, okay? So this is a linearization formula. Okay. Linearization. And whenever, actually I've seen this so many times in physics classes. Had I got $1 each time I've seen this, I would have had really, I would have ate a lot better instead of starving college student. So here's the thing. We have f of x, right? Say f of x happens to be, it works with this kind of particular form, x to some k power. And k does not need to be, k needs not be integer, because in our first example, it was 1/2. You know what I'm saying? So any k will do. And so we have f of 0 is 1 again now, isn't it? We're redoing exactly the same thing. F prime of x, of course, is k, then 1 plus x, k minus 1, whatever that is, right? Okay, and then if I plug in 0 to that, we get k. So Points law form, y minus y1, 1 is equal to our slope, and then x minus. You know what I'm saying? So our y is equal to 1 plus kx. And this is our linearization formula. Good. So in conclusion, this is the formula that your book gives you. 1 plus x to the k power is approximately equal to 1 plus kx for small x. Okay. I mean, there are a couple of problems that requires you to use this, but generally don't memorize it and use it. But you'll see this a lot later, okay, in college and science classes. Okay, so that is all about linearization, and this needs to be pretty close to point of tangency. Okay, I'm going to show you this back to this graph. If you want to approximate square root 5, well, by putting it here, right? It's going to be way, way off, right? However, if you want to approximate square root 5, instead of evaluating this function at 0, 1, guess what point I'm going to evaluate from? You think 2, 4 would be a better place to do this? Because we know exact value of these things at certain perfect squares. So then I'm going to use 2, 4 to draw another tangent line. Then that one will be close. You know what I'm saying? If I want square root 10, then I'm going to evaluate this at 9, 3. So you find the nearest number, right? So we can always do this. It will be close enough. Okay? Any questions before I go to Newton's method? Okay, on Newton's method, this is the idea. Suppose we have a function, f of x, and this is, I chose this because we know the 0 of this thing, right? You know how to factor and do this. And we are going to find the equation of the tangent line at x is equal to 1. Okay, I'll show you the picture. It looks like this. This is a little stretched out, rescaled, but you know what I'm saying? Right here. And that's the equation. Okay, now what Newton's method is, and this is what you have to program, is that we don't always know how to find the 0 of this. In this case, we know because it's factorable, and quadratics, we have quadratic formula. So it's like generally we know how to do it. But this could be any function, any weird function, and you know there's certain equations that you can only solve it numerically with a calculator. And then your calculator has a 0 finding capability, right? And then you wonder how do these people at Texas Instruments program this thing, right? Well, you're about to learn how. Okay. You remember left bound, right bound. That doesn't mean much. You're just giving the search domain. And then guess. It always asks you to guess, right? And then you think about guess too much. You just put whatever the number in between. Unless there are multiple zeros, then it goes to the closest one, right? So that's why the guess matters, but it's like, right? So in this case, our guess is 1. Our first one number is 1, okay? So let's just find the equation of this tangent line first, okay? Okay, so let's come back here. So let's calculate f prime of x here, which is 2x minus 1, right? So instead of this, I'm gonna calculate it like, oh yeah, I'm gonna do it like that. X is equal to 1. That means f of 1, somebody plug in 1 and tell me what you get. And somebody plug in 1 here and tell me what you get. They are not hard, do it fast. You guys are so useless, I want you to know, right? Chance to redeem yourself, this one. 1. Oh yeah, wow, okay. I'm so glad that you can multiply multiply 2 and subtract 1 from 1. Okay, shall we write point slope form? Yeah, let's do that. So we have y minus 1 is equal to y minus 1, y minus, maybe negative, there's a reason I want to write it like this, is equal to our slope, which is 1 and x minus 1. So far, so good. Now, guess why we found this is a linearization, right? We just did. We can call this L of x, but we are not gonna. Okay, why would we do this? Because we can always find the zero of this linear function by setting y is equal to this. It's just x-intercept. It's so easy with a linear function, isn't it? So what we want to do now is set this thingy to 0. That's how you find the x-intercept, okay? But watch this. We have to teach a machine to do this. So I'm going to do it very primitively. So that tells you, let's go to the right a little bit. Our x right here is equal to, is it 1 minus negative 2 over 1? Too much algebra? The reason I want to do it this way is I want to program this part into the machine. You get it? This is how you build an algorithm. Is that too much algebra, or do you understand what's going on? Okay, now the subscripts. See, the first one, we'll call it x1. That's your guess. This will be given by the problem on the quiz tomorrow, well, day after tomorrow. And this is now x2. And the process repeats. This is known as iterative method instead of direct solving. And we do this a lot in numerical analysis. And Newton's method is one prominent way to find the zero of any function. Ready? Somebody compute what this is. And it's not hard, do it fast.
3.
2, right? What? 2?
3.
3. Dang. Okay, I'm so sorry. Okay. Now, so we have to compute this again. So we come back here. So x2 is equal to 3. And that means f of 3. We need somebody. Okay, chance to redeem yourself. Tell me what f of 3 is and f prime of 3 is. People shout it out. It's not hard. Our function is there. Yes.
F prime of 3 is 5.
Oh, you take the prime first. Okay, somebody else. 4. Okay, 4 is correct. Good job, children. Okay, shall we do linearization again? So we have y minus 4 is equal to your slope 5 and x minus 3. You know what I'm saying? I'm going to draw it. I think I can do this. That's this one, isn't it? So at 3, now we compute the new point, and then you draw the line. Good? Now we are looking for that 0 right there. It awfully looks like 2.2 now, doesn't it? Yeah, let's find it and see if it's correct. So here we go again. So set that to 0. Then solve for this x. And that x should be 3 minus 4 over 5a. Too much algebra? Say yes. Somebody tell me this is 2.2. Is it? Okay, and this, we call it x3. You know what I'm saying? And then graphically, yeah, that's 2.2 right there now, isn't it? Oh, by the way, our first guess was when x is equal to 1. First result is 3. Now it's already at 2. See, next one. Let's see. Process continues until we see the pattern here, okay? So now we have x3 to be 2.2. Have a calculator standing by. Now it's going to require a calculator. So we need f of 2.2 and we need f prime of 2.2. Okay. Somebody tell me what these things are.
F of 2.2 is 0.64.
And somebody else tell me what f prime of 2.2 is.
3.4.
Correct. Ready? Here we go. So y minus 0.64 is equal to 3.4 times x minus 2.2. Good? Say yes. Okay, we set this to 0 again. So solving for x here is 2.2 minus 0.64 divided by 3.4, and I hope this is not too much algebra. And somebody punch the calculator and tell me what that number is. Oh, come on.
2.0.
2.0.
1.
Yeah.
1.
11765.
And then we have to change this to squiggly equal to, remember that? Okay. With me? Okay, this is x4. 2.011, this is awfully close to the real answer now, isn't it? The next one is right here. I think I have one more. You know what I'm saying? That thingy. And that 0 is really, really close to 2, which is our real answer. And then when this thing reaches 2, it'll keep giving you the same answer over and over. But I think we have the pattern now, right? Let's build the pattern. This is the algorithm for Newton's method. Okay, let's just pick it up right here. X4 was, this was X3, right? X3 minus, what is this? This is f of X3, right? Divide by, this is f prime of X3. So far so good? Say yes. Well, this is 4 and those are all 3's. So in fact, can we then write it like this? Xn plus 1 is equal to Xn minus f of Xn over f prime of Xn. That's our Newton's method formula. This is what we are going to teach the machine to do. You with me? Okay, take out your calculator and we are going to do this. If my machine listens to me, I can show you how to do this. Oh, there it is. Okay. Okay, we need a starting point. So my first guess was 1, right? That 1. So 1, we have to store that. Store button right here. You see it? Why my big obnoxious pointer arrow? Yeah, 1. And then we put X. We are storing 1 into X. That's our X1. It doesn't do subscripts, so we have to just imagine the subscripts. Our subscripts are here for our convenience, but machines are not that smart. Okay, enter. So this computer is going to remember X to be 1 for time being. Now we have to enter this formula, right? So we'll do X. Oh, wow. How do we do this, right? We do it like this. Remember this is my f of X? Yeah, you guys all know how to do numerical derivative. This machine takes the derivative for you, so we don't have to actually compute the derivative by hand. You know what I'm saying? If anybody wants me to show you how to do this part, raise your virtual hand, then I'll show you how to do it one more time. Numerical derivative. Okay. Okay, here we go. So you're all done entering this thingy, our main function, and it's okay to use a y1 and y2 on your program. Okay, now here, math, and math 8 is the numerical derivative, right? Press enter. Then this shows up, unless you have TI-83. If you have TI-83, raise your hand. So nobody has TI-83. Oh, okay, a couple. I'm going to show you how to do this, then I'm going to write down the command for TI-83. Okay, so this thingy is X, and this thingy is our Y1, the previous, this line, right? So we remember alpha, trace Y1, and then you put, usually you put a number, but it's X, our previous X, which is 1 at the moment. You know what I'm saying? So enter this, and then I'm going to write down TI-83 command here. TI-83 is like this. You enter this. Okay, I'm going to compare the two. So which is which? This means numerical derivative. Math 8 actually has this thing in 84 as well, but it shows up like this to look nice. And this y1 is that y1 right there. This x is that x right there. And this is where we usually put number like 1, 2, 3. That's this x. But in this case, since we are storing that number 1 into x, so we'll just put x here. You know what I'm saying? So 83 people, y'all caught up? Okay. Now, quit. Okay, follow with me. Now we're going to enter this thingy, right? So we're going to put x minus y1. Oh, 83 people, do you know how to put y1? You want me to show you? Raise your hand if you want me to show you how to do this thing, because 83, it does not have this hotkey command. You all know how to do, okay. This is, I'm gonna show you with a y2. Oh, actually, I'm gonna show you with y1, because you don't know how to get there, okay? And this works with the 83 and 84. 84 has a hotkey command, but 83 people, variable, false, variable, number 1, function, and there's your y1. You get it? I'm going to show you one more time. Divide by, now we need y2, which is this, right? This part, f prime, is our y2. So variable, scroll right, y variable, and our y2. You know what I'm saying? Okay, don't press enter now. Whatever you do, don't press anything, just leave it. We need to restore this into our x. See, this is x2. You know what I'm saying? x1 and x2. Machines don't do subscript, so we have to keep track of it. So store and x again, which means it's going to erase this one and replace it with whatever this thing calculates, which will be 3, according to our calculation. Ready? Press enter once. 3. You remember 3? This 3 right here. Next one will be 2.2, but we don't have to retype this whole thing, thank God. If you just press enter, it'll execute the same command again. Press enter once. 2.2, that 2.2. This is how you test your program. You create an easy problem that you know the answer to, and you do this by hand, and then you teach it to the machine and see if you get the same answer. So the next answer, scroll, should be this, right? Okay, let's see if we get that. Press enter once. Aha, that's this, isn't it? That's x4 so far. If you press enter, it'll give you x5. Ready? Here's x5 and x6. Here's x. Oh, really, really, really? You see how it zooms into the real answer? And then x7, we get it. There, exact answer. What happens if you keep running this program? Well, this happens. It gives you the same thing over and over once you get there. So you know when to stop. This goes into the content of this thing called the for loop that I'm about to teach you now, right? Okay, so programming lesson. This is the inside thingy. Okay, that's the entire algorithm of Newton's method. Good. Questions before I give you the program? Okay, program button. You only have quadratic formula, right? Okay. View and name etude. What is etude? Music people, tell us what etude is. Chopin wrote a lot of etude. What are etude? My old eyes, I'm not gonna do new, I guess I already named it before. But while you're doing it, some people tell me what etude means. Oh, come on. Chopin's etude number, whatever. What does that mean? I'm gonna delete everything. So we are here. Etude is not a real thing. Chopin did not mean this to be a concert piece. It's a practice piece for his students. So yeah, in order to increase, right? Sharpen your skills, do this. And then it's like, but then those etudes sound so fantastic. So people play it in concert all the time, but Chopin never really meant it to be a concert piece. That's what etude is. So this is a purely practice program. So I call it etude. You get it? Because we'll never use this. Okay. First, input, right? Let's do input. Program. IO, input output, scroll right. And prompt. We use prompt here, right? Number 3. And we'll call it N. And I believe it's here. Okay. Enter to go to next line command. Now you need another, eventually you will need another input X, but this is etude, so I'm gonna have you figure out how to marry these things. For loop. For loop is the major part of all programs because it's a repetition. See, we have built a loop, right? Iteration, same thing over and over. Machines excel at this. So program button. They're trying to be cute. It's a control command output. Control number 4 is 4. You get it? I know, huh? Texas Instrument people, they think they're cute. So enter 4. Then we have for loop. Okay, here's the syntax of for loop. Number 1, we require an index. We'll call it I. There's I, comma's right here. You know that when you are doing sigma notation last year, I starting from 1 through n. Remember that? Index, A1, A2, A3. In this case, X1, X2, X3. Those are indices, X, I mean instead of N, I, because we are using N to be our final number here. Good? Common indices, I, J, K, and N. Those are like popular indices. Okay, pick, or we'll use I, comma, and this is a starting point. It starts from 1. Most people start this from 1. And our final point, we'll call it N. Because that's this one. We are telling the machine when to stop. That's part of our input. You with me? Let's review. So this is doing this loop exactly n times. You don't have to start this from 1. Some people start it from 0 because some series actually start from 0. You can start it from 2. You can start it from 3, whatever, right? Enter. Okay, here we have to display something, right? What do you want to display? Just I in this? Yeah, let's just display I for now. So program, input output, scroll right, display 3. And then let's put I. Enter. You with me? You with me? And then we have to end this loop. Whenever you start the for loop, you have to have an end so that computer can repeat whatever's between the two. So program number 7 is end. Get it? 7, end, enter 7. Now, so every for loop, if you open it, then you have to end it. So the computer will repeat whatever the command is between for and end exactly n times. You get it? Our etude has been finished. Let's run it and test it. Ready? Quit. It's autosave. Okay, program. Execute your first program, your very first program, unless you're in ComSci already. And ComSci people, this is walk in a park, right? Pay no attention to what I'm doing. Enter. Execute etude. Ready? Bang. You know what I'm saying? Wait, did I get the input? Wait, let me do it one more time. No, I didn't. Okay, something went wrong. Hold on, let me fix it. Your very first program didn't work. 1 through, oh, I put display n. Oh my God, I'm an idiot. Hold on. I want prompt. Why did I put prompt? Okay. Yeah, backfires. Your first program backfired. Okay, let's do it one more time. Program. I was going for the drama, you know. Ready? N. You see, this is how the program should work, right? Prompt, enter n, and then let's put 0. I mean 0. 1 0. 1 0. My keyboard. Okay, 10. And enter. Then boom, that fast. Okay. Are you with me? Now, that's not fun. Let's do something better, right? Okay. Shall we do arithmetic series? You remember that problem that Gauss got? Add 1 through 100? Yeah, let's gonna do that. We are going to do that one. So in order to do that, we need to insert a line here. So second, insert, enter. Okay, and then we need a variable. Yours will be x, but I'll just use s for sum. Uh-oh, where is s? Somebody find an s and tell me. Oh, there, I found it. Oh no, okay. Wait. 0, I need 0. And store that into, somebody find s for me. I think this one, right? Okay, this is known as the initializing. Because I already might have something s, right, in previous calculation, and I don't want this to add on, so I reset this value. Okay, and now I come here, before display, I need to insert, second, insert a line. So s is equal to 0 at the moment on the first loop, right? So I'm gonna put s here. Once again, where is s? There. And then I'm going to add my index I. So s plus I at the moment becomes 1 on the first loop, correct? When I is equal to 1. And I'm going to store that into s again. So s was 0, but by this first loop, it becomes 1. So far, so good? Now, display that instead of this. Let me do something clever here, okay? Open set bracket. Remember arrays? Open set bracket, brace. And then I'm going to put I here, like before. Oh my God. Let's try that again. Let's put I here. And I'm going to comma and then put S. You'll have to think about y, and then close brace, not parenthesis brace. So this is the index notation, S1, S2, S3. S1, S of 1, and will be 1. And then you see this n, it'll go back up, and then I is equal to 2 now, and then S is equal to 1, and add 2, so we update S to be 3 now, and it's going to display S2 is equal to 3, and then we go back up and repeat this process. You know what I'm saying? Okay, I think we are ready to run it. Let's test it. Quit. Okay, if you just press enter, it will execute that program, but now it's updated. Let's just do it up to 4. So we can hand calculate this. Ready? Okay, let's check the answer. So first one is 1. Second one is 1 plus 2, 3. And this one is 3 plus 3. And add 4, 10. Yep, it seems to be working, right? Let's do it one more time, up to 10 now. Yep, 55 is correct. Now let's do Gauss's problem. You see how this thing is going? 100. Enter. You see how fast computer is? It repeats the same command exactly 100 times. Okay, maybe it's not as fast as you want it to be. Almost there. There. How about that? I'm sure it beats doing it by hand. Okay, now I have a little question. Programming question. Let's edit Etude and look at the content. So far, this place right here, then end. So this place is within the loop, right? What happens if I move that display out of the loop? Somebody tell me what's going to happen then.
It's going to bring the last result.
Yeah, it just gives you one final answer and that's it. So if you're a programmer and writing this app for somebody, which way would you do it? The idiot users don't need to see what's going on in each loop, right? So you will put it at the end so that it just spits out the answer, and that's so much faster. Actually, let's do it, right? I'm gonna delete this, and then I'm gonna insert, because that line is longer, and then I'm gonna just put end here, okay? Let's see this. And end 7. Okay, so I reverse the location of end and display, and then let's quit, and then run that program up to 100, and watch this. See, much faster now, isn't it? But it only gives you one answer. And if you're a programmer and general users don't need to see all that action, so this is it. However, programmers do this all the time. When they are writing the program, because something always goes wrong, like I did earlier. So you want to put this thingy up here inside the loop for you to debug. You want to see and to test it with a small number, and you have to compute those answers by hand. So you originally start this display inside the loop, and you run it and test the answers many times and do a beta testing. And if you have confidence that this is good, then you move it out. You know what I'm saying? But for our purpose, is I'm gonna make you give me multiple answers. You might just want to leave it inside, okay? So this is how the quiz is going to go. You take a picture of this screen. It's a really short program, right? When you turn in the answer, you don't even have to write this down. And then you take a picture of this screen, your result, right? Not this final answer, but the bunch of the answers, right? And then you put those two together into a PDF scan, you know, Office Lens or otherwise, and then you turn that in, and that's it. I mean, this is the easiest 10 points you will ever learn. And the whole thing should take less than 10 minutes, like 5 minutes tops. If you have a program that works, you can do it in like minutes. Don't try to figure it out tomorrow because, I mean, Thursday, because you're going to run out of time. You get it? Questions?
Does it matter why the second answer is 101 and the first answer is 100?
Repeat, you're breaking up.
Like the second answer, that's like the bottom answer on the calculator, it says 101 and the answer above it is 100. Like, does that mean anything?
Oh, something went wrong. Oh, I see. Oh, I'm so glad you caught it. This is kind of debugging process. What that does is this for loop, when it goes to the end, this is when it updates and already updates to the next one. So it's like, we don't want to do that. We definitely want to keep it right here. I'm so glad that you caught this, and this is part of the recording, okay? So you take a screenshot of this and give it to me, and let's run this one more time. Let's just do it up to 10 or 100, whatever, right? And then you take a screenshot of this and give it to me. Now it's back to 10. You know what I'm saying? Because when it hits the end command, I mean, different computers do it differently, but this one must be updating that index to the next one already before it goes back, and not at the beginning. Huh, I did not know that.